Hello. Hi. Hello. It is good to see you. This is lecture 8. Lecture 8. Yes, and we're doing something very exciting. We are now sliding off of force for the moment, but using those force concepts, the idea of why things move, and sliding into this other concept that comes as a result of motion. Well, what is the result of motion? You start here, and then when you move, you end up here, right? That's motion. You move, right? And so the idea that we're going to be talking about in this lecture and the next lecture is about how we write down or how we calculate or how we figure out or how we express where you are. Okay. So in the same way that the first lectures that we've been talking about up to this point, past few lectures, have been about why do things move? And we know the answer is force, right? And Newton's laws and things like that. Getting back to all this stuff, right? Very valuable stuff. We are now going to take the next step and say, well, okay, I know how I move. Now, where am I? And when am I? Okay. So the idea of where and when is very interesting. In physics, you have to understand that we think of not just like where we are is just in length, width, or height, but also in time. At any given moment, you are at a location. Does that make sense? So how far away you are from some starting point, some location, okay, is an issue that's really important in physics. Now, this stuff is not anything that like you don't know. As with most of the physics that you are doing in this class, you've experienced before. You know what it's about. It's just a matter of expressing it mathematically, right? And that part is really, really important and valuable. And like any other language that you're trying to learn, practice, practice, practice is the key, right? So being able to do this kind of math on a regular basis, if this is what you want to do, is important. That said, you know what? The concepts are really, really important too. So I'm going to give you some concepts, and right away, because the math stuff and because the calculations of where you are, right, is so important, I want to go right away in this lecture to start giving you some ideas of where you can look, okay, and what you're going to be doing in addition to watching this video to understand the concept of where you are, okay? Now, I'm going to show you right now by sharing my screen and showing you what kinds of things you're likely to be using, okay? The first is this, and you've seen this before, the physics in motion videos, okay? Now, like I said, the physics in motion videos are really good at expressing a lot of concepts and ideas with a high level of production in their work. And so you're going to be looking at things like segment A for this describing motion, unit 2 in the physics in motion here. Here's the URL up here, right? Segment A, the difference between distance and displacement. And then B, the distance between speed and velocity. And then segment C, which has to do with acceleration and kinematic equations. Okay, now this is stuff that we're going to be doing in this lecture. And then in the next lecture, we're going to go on a little bit further to graphing motion, or the concept of that, and the ideas of relative velocities, and the idea of horizontally launched projectiles. Again, sounds complicated, but actually isn't. You've seen this all the time in your life. If you've ever watched a baseball game, if you've ever tossed something into the air to your pals or anything like that, it's all stuff that you know, but you might not have expressed it mathematically before. Okay, so make sure that you do these. This will be mentioned in the study guide. These are the physics in motion videos, unit 2, describing motion, that we'll be talking about for this lecture. Now, I want to also mention that this college physics textbook is really important for this as well. Let's go back to the OpenStax College Physics. I'll go back to the beginning part so you remind yourself this is what the URL is, openstax.org, details books in college physics. And if you look at the table of contents, you'll see that chapter 2 here, this stuff, especially 2.5, Okay, up to 2.5. This is the thing we're going to be talking about today in this lecture, but you got to read it to get more information about how to do it and explain it mathematically. All right. And then next lecture, we'll be talking more about these kinds of things, chapter 6, 2.6, 2.7, and then chapter 3 here. Okay. So you got to make sure to see this stuff. And so make sure that you look at these. We'll revisit these a little bit later in this lecture, but I wanted you to see them right now and be aware that you need to use the College Physics OpenStax textbook, and you'll need to use the GPB Physics in Motion Unit 2, okay, after you listen to me and watch the things that I do right now. Okay, so that's really, really important. All right, and let me again, one more time, because I don't feel like I can say this enough. The math is going to be possibly a stumbling block, an obstacle for your understanding of the concepts. Okay, that's okay. Like I said before, math is just a language and a basis, a fundamental aspect of all science, but especially perhaps physics amongst the sciences like biology and chemistry and stuff like that. The math is really, really important in understanding how we go about explaining and doing and calculating these things. It's very valuable and very useful. But if you're not familiar with it, it can feel daunting. It can feel like an obstacle. Okay. And believe it or not, this actually happens for all physicists. Even Albert Einstein, he himself, most famous physicists possibly ever, right? Certainly in the 20th century. He once wrote, he said, look, math is hard for me too. And I actually have a hard time with it. Now, some math I can do pretty quickly, but when I was really trying to think about how to do the physics of like relativity and space and time and things like that, I didn't have enough math. And my problems in math are hard. And so that's the kind of barrier that everyone might run into. So I want you to sort of be aware of that and don't worry. Practice makes perfect. There are some people who, like, let's say you're a physics major or a physicist, okay, then you're doing this math, and this is very, very important. You got to get all the math all the time, and you just got to practice and practice and practice, practice. Okay, this physics class is a means to an end, is a little bit different, right? It's concepts and ideas that will help you move forward as you're doing other stuff in your life or your career or in your academic work and so forth, right? So you need to know the concepts and you need to know how to do them. You might not be able to do them so well, maybe a physics major might, but don't worry about it. Do this math. Do not be afraid of it. Try it, keep at it, and if you want to be good at it, practice makes perfect. Lots of practice problems and questions to do. Okay? All right. So if you understand that, then we are on the same page. Let us get going on the concept of where we are. Okay? Let's just first ask ourselves, where are we? Okay? I am here, right? And also, when are we? I am here right now. Agreed? Okay. Let's say I am at this location, right? A certain distance to the east and a certain distance to the north and a certain distance up or down from that spot in the room. Does that help you? Well, if you were right here, you could see the spot in the room, right? That would be fine. But the problem is, like, where do you measure yourself from, right? That's really, really important in physics. This is the first thing that I want you to understand, and is a distance and displacement, okay? The idea of how far away are you from something else is actually extremely valuable. And we have to refer to that whenever we're talking about where we are in the world, in the universe, or in this room, for example, okay? So this is the first concept I definitely want you to understand. Distance, you understand distance, right? Well, 3 feet, 5 feet, 10 yards, 100,000 miles, right? That's distance. Distance doesn't really have a direction. It's just a unit of length, right? But if we want to be more specific about where are we, right? Where are we? And where are we now compared to some time in the past? Or where will we be compared to where we are now, right? Where, though, requires this concept called displacement. So displacement is just a fancy word for saying where the heck are you compared to somewhere else. Okay, so displacement, how far are you displaced? Now, again, you want to be a little bit cautious because there are some other times you use the word displacement, like you have a rock or something and you put it in a bowl of water and it displaces a certain volume of water, which is unfortunate that you have to use the same word for a couple of reasons. But this concept of distance and displacement is really, really important. Okay, so how do we say that? We set a location, okay, put a spot, and often we call that the origin. Right? If you're just doing math, like there's a graph, often the origin is like where x equals 0 and y equals 0, right? The origin. But you find a reference point. When in physics, an origin is just sort of a reference point, a certain location in space and time where you can say, well, assume that that is like the starting point. Okay, so for example, maybe you like the Eiffel Tower or the Statue of Liberty, or pick a place, right? The corner of this boulevard in that street, or something like that, or just this end, the Staten Island end of the Verrazano Bridge, like right under the pier, right in that spot right in the middle. In other words, pick a spot, right? That's your origin. And then you can measure where you are with respect to that location. How far have you been displaced from there? Where are you? How far away are you? And in what direction? Okay, so understand the difference there between distance and displacement. So distance is just a scalar quantity or a total amount of travel or something like that. Whereas a displacement is a vector quantity. So you actually need to know where you are with respect to the directions, east, west, north, south. Right? Remember, we talked about vectors having both magnitude and direction. All right. So displacement is a vector. So let's just set something up. Why don't I just put a certain point here? Dum, 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 and let's say that that is my location. Where am I at this moment? Right. And then the where I am compared to the origin, this space here, okay, is what we might call the displacement. And of course, we use the lowercase d in this case for displacement. And of course, this is confusing because distance also starts with a d. So you have to be a little careful. And this is where things, like right off the bat, right, things can start getting confusing. Don't get confused. It's really okay. It's quite straightforward, but just understand that that's the point. Okay, so that's where we're talking about displacement. Now we have to figure out like how we express that displacement. Well, in physics, we would just pick a unit of distance and a direction. So if I would say that this coming this way, if this is the origin, let me say that's the positive direction. Okay, positive direction going this way. And since it's horizontal, usually if you've learned in math class, usually the horizontal axis is the x-axis, right? So we can say that in the direction of the x-axis, the displacement d, lowercase d in this case, or could be uppercase, just, depends on who you use or who you talk to. The displacement is this many units, say, whatever some number of centimeters or a certain number of meters in the positive x direction. Okay, so far so good. Okay, so let's just start with that concept right away. I'm going to say, where is your displacement? What is your displacement? Well, what is your displacement now at this moment, right? As opposed to your displacement in the past. These are two different things. Oh my gosh, how annoying. I mean, but that's okay. If we're talking about at the moment of time equals 0, okay, then we put d, a little 0 after it, right? So displacement at time 0. So this means d sub 0 or anything sub 0, right? In this case, d means displacement at time 0, like at the time that we start counting. At time 0. And this is what we so often don't remember about motion, Remember I talked about, I was saying, where are we in both location, like space, and time, right? We're trying to figure out that all the time. Excuse the pun, but basically, we're always trying to figure out where we are compared with a certain time in the past, right? That motion is the concept of displacement after a certain amount of time. So d0 would be the displacement at time 0. If I start right from the origin on that location right there, right, and I refer to me starting point, my starting point as the origin, then d0 is just 0. Yes. But what if I start, say, I'm going to say that that spot over there is 0, and I start this many meters over in this direction, then your d0 is not 0. It would be some number like 3 meters or something like that. Does that make sense? Okay. So, makes sense? If I were just saying, okay, how far away are you from that location at this moment, at time 0, before you start moving? Okay. 3 meters in the positive x direction. Done. Yay. All right. So far, so good. Now we add the second twist. The second twist comes from Newton's first law, right? P equals mv. Momentum is mass times velocity. Now, we've already talked about velocity. Yes, velocity is how fast you're moving in a certain direction. Well, how does that affect where you go? Let's say my velocity is, I'll say I'm driving a car in a speed zone or something, and I'm going 25 miles an hour, right? And I go for an hour. How far have I gone? 25 miles, right? No big deal. Let's say if I'm going 30 miles an hour and I drive for an hour, how far I go? 30 miles, right? Yeah. I drive 30 miles an hour for half an hour. How far do I go? Well, I'll just take a half of an hour, 30 times a half, and that's 15 miles. This is pretty intuitive, straightforward, right? Similarly, we, instead of using miles per hour, we can just use meters per second, right? Let's say we're moving at 3 meters per second this way. Great. Then that means that in the first second, I will have moved 3 meters. In the second second, I've moved 3 more meters. In the third second, I've moved 3 more meters, right? 3 plus 3. And so if I've moved for 3 seconds at 3 meters per second, that's 3 times 3 is 9. And so I have moved, my displacement will have increased by 9 meters per second in the positive x direction, going x that way. Make sense? Okay. So at time t equals 3 seconds, I will have moved away from my original location, right, which was d0, my displacement at time 0, the amount of speed that I had multiplied the amount of time that I'm moving, right? That makes total sense. So let's say at the moment at time 0, right, I am moving at a certain v, which I will put as v0. Makes sense? And that's the same thing as just saying velocity at time 0. And okay. And that would mean that the distance that I travel after a certain period of time, t, right, is just how fast I'm moving times the time. So far, so good. So let me just write that down. V0 times t, right? That's displacement at time t due to the velocity, right? Due to the initial velocity, due to v0. Makes total sense, right? Okay, so far so good. Now, I want to try something really cool for you. I want to show you something really neat, all right? I'm going to use a graph. Now, I don't know if you guys have seen graphs like this before. I'll bet you have. Like, you've done graphs like all your life, right? In math classes. So I'm going to graph. All right, so this is my graph. Instead of x and y axes, right, I'm going to use time as time goes by, right, coming this way. So I'm going to make this t time like that. And then I'm going to say this vertical axis, instead of you being like just some y, I would say it's the velocity as a function of time. Okay. So velocity here can change. Velocity could be 1 meter per second, 2 meters per second, 3 meters per second. But I didn't put the zero at it. Remember the zero? Remember I put the zero down, v0, meaning the velocity at time zero? I'm not talking about velocity at time zero at the moment. I'm just talking about velocity in general, okay? And what I'd like to do is to graph my velocity as a function of time. Now, why would I want to do this? Well, everyone wants to measure stuff, right? If you're doing like an EKG, right, as you've seen that kind of thing, like your blood pressure or something like that, or over time, or measuring anything sort of vital sign, you want to see a graph of how it changes over time, right? If there is a change or what kinds of things happen, or if it stays steady, a graph is really, really helpful. Just like when these like the paper strips nowadays, it's all digital, right? But you can sort of see, oh, this is the person's heart rhythm, this is the person's blood pressure as a function of time, etc. Those kinds of things. So graphing is extremely useful, and I'm going to graph this thing right now. And this time, we're going to graph that question that I said earlier, right? Let's graph. You're going at a velocity v0. So now I'm going to measure this v0. So I'm going to say v0 happens to be this number here, v0. There, that's it, okay? And what happens is that for zero, for a period of time t, okay, so this is the t-axis. So I get to some location, there's a time. Let's say I pick a time t. So this was time 0, right? That's the origin. At time 0 to time t, 0 to t, 0 to t. So far, so good? Okay. Work with me. Follow me here. This is cool, all right? I think it's one of the neatest things about physics. If I go at the velocity v0, right, all the way till time t, makes sense? Let's say if I said like 3 meters per second for 3 seconds or something like that, or I could go 10 meters per second for 4 seconds, or I could go 40 miles an hour for half an hour. I don't change my speed, right? Then that would mean that this graph, right, the speed, the velocity, I should say, right, as a function of time stays the same. So I would just basically have a straight line going across to here, okay? That would be my function. Velocity is a function of time, just a straight line going across all the way till time t, right there. Okay, make sense? All right, here's the cool part that I want to show you. And you might even look at it and go, well, duh, that's obvious, right? That's something that we got used to. If I look at the space under the graph, so here's the line, the function, right? The velocity up to time t. If I look at the area under the curve between this axis and that function, let me just look at that area here. See that area? What's that area? Well, you know that the area of a rectangle is the length times the height, right? It's just 2 dimensions. So it's, well, the length is from 0 to t, right? And then the height is from 0 to v0, v0, we call it v0, N-A-U-G-H-T, meaning the 0 there. So from the origin to the time t, that length is of that segment, right, is t. And then from 0 to v0, up vertically, right, that distance is v0. So what is the area of that shaded space? Well, you guys know how to multiply rectangles, right? Get the area of rectangle. It's v0 times t, is it not? Yes, it is. So I'm just going to draw that in there. The area equals v0 times t. Where have we seen that in the last 2 minutes? Check it out. The displacement at time t due to the velocity v0 is v0 times t. The area under this curve is V naught times t. Coincidence? I think not. Indeed, it turns out that if I do a graph of the velocity, right, and for whatever period of time, the area under that curve during that line segment from time 0 to t, or from some time t1 to t2, or time t2 to t3, that's how far I go. That's my displacement. Pretty cool, right? This displacement due to velocity. So that cool tool, the idea that you can just measure the area under the curve and you can get the distance if you have a velocity in the vertical and the time on the horizontal, is very useful for the next thing that we're adding to this displacement thing. And this displacement thing is the Newton's second law of motion, F equals ma, right? What is A? A is the acceleration, right? Remember, when you push on something or pull on something with a force, you change its momentum, and therefore you change its velocity if the mass stays the same. So that means that A changes what V is, right? How does it change it? Think about this. Let's say I'm starting my car and I'm at the stop sign or something like that, and I start moving, all right? And I accelerate. 1 second later, I'm going 10 miles an hour. 2 seconds later, I'm going 20 miles per hour. All right. 3 seconds later, I'm going 30 miles per hour. So how fast am I accelerating? It means that every second I'm accelerating, I'm going an additional 10 miles per hour. Make sense? Okay, so the acceleration rate of my car is 10 miles per hour per second. See? So, you know, like sports cars, they're like, oh yeah, I can go from 0 to 60 in 4 seconds or something like that, right? Well, what's the acceleration if you're going from 0 to 60 in 4 seconds? Well, that's 60 miles per hour. If I start from 0 to 60, that's 60 miles per hour. That's the velocity change divided by 4 seconds. So it's 60 miles per hour per 4 seconds, or in this case, 15 miles per hour per second. See, that's just an example with a car that I'm talking about. Makes sense. Well, if I'm doing it in physics class, right, I'm not going, again, like I'm going to try to keep it with the same units. Instead of talking about miles per hour per second, we're just going to do meters per second, right? And that's what we were talking about earlier, meters per second, but we're talking meters per second, right? Remember we were talking about miles per hour per second? We're actually talking about meters per second now. So we have an acceleration, right? Is normally in units, as you've seen already before, of meters per second, or written as meters per second squared. Same idea, right? Meters per second. And that's the acceleration. So if I just put acceleration, now interestingly, we don't put the A0, okay? In fact, in some physics classes, as you go more advanced, you will sometimes just put the A0 because the acceleration will change over time also, right? So your acceleration will change over time, but right now, for the purposes of this class, we're just going to keep the acceleration to be the same, okay? It's just acceleration all throughout. It's the change in velocity. Or I'll just put rate of change of velocity. So how do I get my velocity after a few seconds? So if I have a certain acceleration, remember I was saying, like, you know, if I'm going at, I'll go to meters per second instead of miles per hour. Remember, if I'm going at 0, then I go to 5 meters per second in 1 second, right? And then I go to 10 meters per second in 2 seconds, or 20 meters per second in 4 seconds. Then my rate of acceleration is 5 meters per second, or 5 meters per second squared. So after a certain time t, how fast is the thing going? Can I figure that out just using the acceleration and the time? Well, why, yes, because my speed, or my velocity, excuse me, after I get started, right, the amount of change in my velocity will be how much acceleration I have multiplied by time. Oh. I'm going to write that down, right? This is just the math that I'm talking through right now. It makes sense. And in the videos and in the textbooks, there will be more discussion of this. So don't worry. Just to explain it this way. So AT, right, is the velocity at time t due to, oh, I'm running out of room at the bottom here, but I'm going to try to write it in so that it can all sort of show up in the same space, due to A. All right. So if you have a certain acceleration, then if you multiply the acceleration and the time together, you'll get the velocity where you are at any given time. Okay. So these numbers, these things here, they kind of add up to create a very interesting circumstance, right? You have a displacement at time 0, you have a velocity at time 0, and you have acceleration at time all, right, time 0, but also all the rest of the time. And then you have v0 times t is a displacement at time t due to v0, right? And then you have at is the velocity at time t due to a. So this now gives us some really cool options. Let me just go to this other cool stuff, which I cannot let go of because this is super cool, right? Velocity times time is the area. In this case, the velocity stays the same. But if you're accelerating, then your velocity changes, doesn't it? So what happens in that case? Wow. Well, let's get to it. How fast am I going to be going? Let's say I start, right? My initial velocity, I start v0, not at 0, but like let's say start at 10 meters per second. Okay. Well, then what'll happen to my velocity if I start accelerating at that moment? I'm already going 10 meters per second. Then accelerate from there for a certain number of seconds. Well, the initial velocity, right? That's like time 0 plus the amount of velocity I now have at time t due to my acceleration. If I add these two up, that's where I wind up in my velocity. Doesn't that make sense? Right. So I start at 10 miles an hour or 10 meters per second. I'll stick with meters per second here. Start at 10 meters per second and accelerate at 5 meters per second squared. After 1 second, I'll have 10 plus 5. Right? After 2 seconds, I'll have 10 plus 10. After 3 seconds, I'll have 10 plus 15. After 4 seconds, I'll have 10 plus 20. That's my velocity after a certain amount of time, right? So watch me write this. The velocity at time t, the velocity at time t, all right? So I'm just going to write that down so that we can remember it. Velocity at time t. Velocity at time t is the initial velocity, right? The initial velocity, this one, velocity at time 0, plus at. Yeah, it's just the acceleration at, how much you have changed because of the acceleration. So the velocity at time t is v0 plus at. Just these very same at's back here. Okay. Now, what about how far I've gone? How far will I have gone if I have accelerated, right? I started here. And remember, if I were just going at v0 for a certain number of seconds, the area under this curve is the distance v0 times t, right? But what if I start at v0 and I go faster? I'm accelerating. I'm going up, right? That's the acceleration. So the line here that was straight isn't straight anymore. Oh, wow. That's going to suck, right? No, it's not. It's great. It's easy. I'll start with a very straightforward example. Let me just draw these again, okay? Like that. I'll draw this axis a second time. A slightly different color, but it's the same idea. All right. Let's say I start with time 0 and I go till time t. Right, that's the amount of time going. But this time, if I start at velocity of v0 of 0, I start nowhere, and I'm just accelerating, right? Remember, I take my acceleration, my a, and multiply it by the amount of time. And so if I use this v time at certain time, right, vt is v0 plus at, and my v0 is 0. Let's just use that as an example, right? My v0 happens to be 0. Ooh, what will happen in that case? Well, I'm just going to graph it, right? Let's start. So once again, this big axis is v, and this axis is t. And I start at 0. And if I keep going up, what am I going to be doing? Let's see. In the first second, I'll be, say, something like that, right? I'll go a certain rate. That's the a times this amount of t. And then the next second, I might go something like that. And then the next second, I might go something like that. And the next second, I might go something like that. So, like that, right? That might be the velocity starting from 0 and then accelerating and getting bigger and bigger and bigger until I get to this point, right? That makes sense. If I'm speeding up, right, my rate is going up. So I have this slope here coming up this way, right? Now the slope of this line is a. And I don't have to show you that mathematically, but a times t is the final velocity, right? V equals v0 plus at, and is 0. So at this point up here, this spot, right there, right? That happens to be at right there. See, at is how fast you're going if you're accelerating for a certain amount of time. Ooh. Now, if that's the case, can we use the same trick? Yes. What are the area under the curve? The area under this segment is actually the distance we've traveled. Again, same kind of thing. So I just now have to figure out the area of this triangle. You guys remember what the area of a triangle is? Yes, it's 1/2 base times height, right? So what's the base? The base length is t, right? And what's the height? It's at. So 1/2 base times height. So the area under this curve, I'm going to draw it again in here using this. The area under this curve here, 1/2, right? Base times height. 1/2 times t times at, right? 1/2 base times height. And I'm just going to write this a little bit more compactly. Instead of calling it 1/2 TAT, I'll just say 1/2 AT squared. Whoa. So the area under the curve, remember the distance that we've traveled, right? Due to this velocity, this acceleration is 1/2 AT squared. I'm going to write that down. This sounds very useful, doesn't it? So 1/2 AT squared equals the distance. Let's see, we'll call it 1/2 AT squared equals the distance. Oh, wait, it's all in the same direction, right? So we shouldn't use distance, we should use displacement. Yeah, let's use that word too. So let's just be really clear and not even use distance. Let's just use displacement, okay, at time t due to the acceleration. The displacement at time t due to a. Makes sense? Yes, I hope it makes sense. And then the crowning achievement. Well, not quite. The penultimate achievement. The pen crowning achievement? How far, what is the displacement due to the velocity? Remember, We already put this down, displacement at time t due to v0. And then this is the displacement at time 0. And then we just said that 1/2 at squared is the displacement at time due to the acceleration. Whoa. We can add all these things together. So displacement, all right, this is super cool. Okay, displacement, the total displacement at time t due to all these things that were described, all of these things, is the addition of it all. Okay, here's what I'm going to write it down. And this can be written in many different ways, but I'm just choosing to write it down using the technology or the terminology that we have set up over here so far. Okay, the displacement at a certain time. So I better write down that time t just to be sure here, because I wrote so fast that I skipped at time 2, right? I gotta write time t, not time 2. Oops, at time t due to all these things is, and I'm just gonna use the term d again, but this time the displacement, and I'll put the little t after just so you know that it's at time t, but you can use it in many different ways. You can use different letters, whatever letters that are useful in your mind or a textbook uses to make it happen. Adding them all up, right? First, we take the displacement at time 0, where you were before, 0, and then I'm going to add the velocity displacement, the displacement at time t due to the initial velocity, right? Velocity at time 0. So that's d0 plus v0 times t, like that, okay? Plus the displacement at the time t due to the acceleration, which we just figured out, right? Which is the area under that curve. So that's plus 1/2 at squared. Whoa. This equation right here, right? With all these different pieces, you know, all the way down this side here, and then over to this side, right? Velocity and displacement. This equation can show you how far you are displaced if you're moving in one direction along, say, the x-axis in this instance, but it could be other equation, it could be other axes as well. This is so cool that I'm going to box it with this red marker, like that. dt equals d0 plus v0t plus 1/2 at squared. And then, because it's so extra important, I'm going to box it a second time. I'm going to put a green line around the red line, like this. Yeah, all right. So look at what's happened here. This equation basically tells you where you are, right? Along this line, if you have a velocity, you have acceleration, at time t, at any time t, this equation gives you what you need to know in terms of your displacement, right? This is super useful. And yes, there's math involved. And you could, and in fact, many people do. In fact, when I first learned this physics, I learned it just by the math. I only memorized the equation. I was just told that if I remember this equation, d and v and what a and what t are and things like that, I could always figure out where I was in the displacement, in the direction, right? Because it was expressed by this equation. But I hope what we've done here by talking about it is to understand, have you understand what all these different pieces mean and why this equation works and why you can put it together. And this trick, this aspect, right, of being able to figure out the area under the curve of velocity versus time and figure out how far you've traveled, well, that is deep, even though it may not seem deep because it's just a couple of, a triangle and a rectangle, right? But if you take calculus ever in your life, maybe you already have, you will recognize this is one of the most fundamental and important applications of calculus in real life. Yes. Why is calculus important? in part because you can use it to figure out your distances, okay? That's cool. You can figure out your displacements. You can figure out where you are at any given time compared to any other location in space and time. That is cool. Okay, so this is the end of this lecture. Thank you so much for sticking with it. You understand that, of course, you should be writing down your lecture notes, study guides, filling them out as you're doing it. If you have any questions, ask. You may have seen some of the applications of this in the lab class already, or maybe recitation. Be ready to think about it some more and go back to those other videos. Okay, once again, I will share my screen one more time to remind you what videos and what textbook stuff you should be looking at. All right, in the college physics textbook, all right, the equations of motion are really important. When we talk about motion equations, all right, this is what we're talking about here. In section 2.5, notice it uses delta t, like the change in time, delta x, the change in x, delta v, the change in v. You said the x zeros and the v zeros, and see how acceleration, they talk about being constant, so a doesn't give a zero underneath it. But look at how they use math, right? The straight mathematical stuff, algebra here, to figure out the equations that we did using the combination of just the mathematical addition and the area under the curve and that geometric way of doing things. Okay, read through this. This is actually really, really important. And look, they got the same equation that we did. V equals V0 plus AT, right? And then you go even further. Oh, look at that. We got the V0 by AT. There's an example that you can do. And then if you want to go even further, whoa, check this out. Using their mathematical techniques, they also get 1/2 AT squared. Now notice that they use X, whereas we used D, right? That's okay. They're using X because they're assuming you're moving in the X direction, which is 100% all right. If you are doing your homework or something and you use X and X0 instead of D and D0, I'm 100% cool with that. All right. So this equation and all of these exercises and practices will give you a sense of exactly how this all works, right? When the velocity is not constant, and oh, look, they use extra math, which is very useful, to give you yet another useful equation that you can play with, okay? So these are all sort of versions of the same equation, kind of moved around with the different letters in such a way that you can figure out what you're doing. And so here, this is what we call all those equations that we talked about, right? Average velocity, the assuming constant acceleration, for example, you have your displacement as a function of time, you have your change in velocity or total velocity after a certain amount of time, you have your distance. Remember, you can use X or D or any other letter that you want. Okay, in the next lecture, we'll use more than just one letter, which makes it even more interesting. And then you can start making all these calculations. Okay. And then here's an example. We'll probably use that example 2.12 more than once, right? How far does a car go when coming to a halt? You're driving along, suddenly, yeah, deer jumps out or something. You got to stop, right? Or, a ball starts bouncing out, and you know that when a ball comes out into the street, a kid may well be following it, and you got to stop, for safety's sake. How does it work? How do your brakes work? How does that all turn out? Turns out that this works. You can add your velocity, right? This is what we're talking about, increasing velocity, but we can also decrease velocity too. We'll talk about that in the next lecture. But in the end, this is very, very useful. And the equations of motion in section 2.5 are expressed very nicely, but do read sections 2.1, 2.2, 2.3, and 2.4 if you want to get a deeper sense of these kinds of things. And then here's the units for describing motion, the gpb.org physics in motion. A, B, and C segments in the unit 2 are going to explain this stuff in greater detail for you as well. Okay, so make sure to do those things, do your study guides. I hope you've already done most of your study guides now. This is a long-ish lecture, but I hope it came across to you how cool this aspect of motion is, and not just like causing it, but now we know where we go. Where are we going to get after a certain period of time if there is a force, or if there's an increase in momentum, or if anything like that involved? Cool, right? I think it's cool. Okay, thank you so much. I will see you in the next lecture, all right? Thank you so much. Bye. See you later.